Thank you very much. And it's great to be here with everybody from the CBC community. And it's equally great to see that the community has stayed so strong throughout these few years. I mean, I remember the first time I worked with Abel a few years back on the topic of blockchain. We were looking at cybersecurity. And it's really nice to see so many projects are coming to fruition in the built environment, applying blockchain and smart contracts. But my project today that I'll be discussing is our ongoing research project Restore that we have done with University of Cambridge and the University of Birmingham. It focuses on reuse of steel. Although we haven't explicitly used blockchain, I think it will be relevant to a lot of the people on today's call because there's potential to extend this work into those domains. And so I would welcome everybody, if you find this project applicable to what you have developed so far, to follow up with a discussion with us on how we can extend this project to incorporate your expertise on blockchains and smart contracts. So Project Restore is really focusing on the reuse of steel in the construction industry. I'll give you an overview of what we've done so far with that project, how we've embedded generative design for structural engineers, and how this relates to digital twins and blockchain applications. So as you may all well know, the steel industry already significantly contributes to greenhouse gas emissions. Although, most of steel is recycled in the construction sector, there is very little amount of steel that is actually reused. So typically, we recycle up to like 93% of our steel in the construction sector, but in terms of reuse, only between 7 to 13% of this is reused in construction, which means that there's a huge gap there. There is a potential to reuse more amounts of steel in new built projects, particularly in commercial developments and in industrial buildings. So that's what we focused. It's really targeting the iron and steel construction sector, which is currently the fourth largest global CO2 emitter, about 2.6 gigatons estimated in 2019. The way we've chosen to tackle this is through digital information and digital information management, digitally twinning steel members and their performance over lifetime. So it's really a combination of two domains of expertise. University of Birmingham with its expertise on non-destructive testing of materials and doing particularly the digital twinning of steel members and their performance over lifetime, and then combining our expertise from Cambridge, from the CIT lab, to translate those digital twins into new designs of industrial and commercial buildings. So this is a research initiative funded by the EPSRC. It's valued at 1.3 million. It's a collaborative effort of a 3-year-long journey. We're now in the last year of this project together with the Birmingham team. And a key outcome from the Cambridge side is actually to help develop this web-based design tool that can be harnessed by structural engineers to embed reused steel members. But it has a potential to actually also involve the steel suppliers. So we really think that although, us as researchers, we develop tools up to a certain level of technology readiness, a big gap that we see in the market is actually the business side and the business model, and helping the construction steel suppliers to be able to quickly capture their stock of reused steel materials and connect that to the designers who are then designing a new industrial or commercial buildings where those reused steel members could already be incorporated at the early design stages. So the Restore team from the Cambridge side comprises of Professor Ioannis Bourilakis. He is the principal investigator from the Cambridge team side, myself, and Dr. Sohaila Koukalani. And she has been doing most of the great efforts that you'll see today around generative design. So the Cambridge team has really spearheaded the development in this project on using and integrating BIM into the seamless inclusion of reused steel components for the design of new industrial, residential, and commercial structures. Whilst the Birmingham team is focusing on the actual digitization and testing of existing steel frame components and creating a catalog of steel beams that we can then use and test in different types of scenarios. Here's a quick overview of some of the work that the Birmingham team is leading. So really what the Birmingham team is trying to do is characterize the steel beams materials in order to actually align what is being tested in the real world with the simulated models. So to try and minimize that gap. And that really is the part that many of us may have heard of, which is the fidelity of the digital twin. We're trying to really capture the essence of what happens to the steel beam members in a machine readable format to have as much of its performance data in digital twin format for us to then integrate into the design tools. So a lot of that is actually dealing with lab-based testing and capturing the types of conditions that you might already have on existing steel beam components like dents, which may result from deconstruction processes, which are characterized by various properties such as location, magnitude, direction. So all of this needs to be captured within that lab-based environment. They have also, in addition to these types of common dents, tried to capture and replicate, corrosion type of tests. So corrosion tests are being ran and then characterized into those steel frame structures. So there are different methods that are being used to capture the existing conditions of these steel members, as well as doing additional tests within the labs using various sensors like LVDTs. These are outside of my remit of expertise, by the way. This is what the Birmingham team is dedicated the last 2 years, is doing a lot of this lab-based testing. But in essence, what we get to is a digital twin of the beam, right? We want to get as realistic of a characterization of that beam's load capability in order to then be able to embed that into any future designs. So a critical part of what the Birmingham team is then able to produce to us is actually a better understanding of the characterization of these steel beams in order for the steel suppliers to have better confidence in assessing whether or not those steel beams can be reused. A lot of that assessment still to date happens very manually. And so a lot of steel is discarded as non-reusable as a result. So where do we come in? The Cambridge team comes in, especially on the generative design tool front. What we want to do is take this catalog of steel beam members alongside its performance related information and load bearing capacity data and embed it into the design tools that structural engineers can use. So a big part of that is to be able to create a generative design tool that can then incorporate different sections of those steel beam components. So for those that may not be familiar, generative design is sort of an iterative design process that can generate a wide array of design options for designers. This could be architects, but in our case, structural engineers. And this is taking into consideration specific constraints and objectives that you can set. Typically, you have 3 main components in generative design: exploration, where you explore the entire design space for generating wide range of design options; iteration, so you can do numerous iterations of the designs fitting those constraints that you initially set up; and then optimization, so finding the most optimum solution for your design. So you can imagine what we end up is we have a catalog of steel beam members that can then be utilized into the design of new steel structures. So we can imagine that you have these catalog of steel beams, we've mapped them, we've digitized them, we have now an understanding of how they will perform. This is after deconstruction. We then want to do is match those steel beams. So what we're trying to do, our goal is really to match the demand elements with the supply elements. So this goes more into the maths, but I'm not going to bore you with the maths. But essentially what we're trying to do is match the pairs generated by 4 different algorithms: greedy algorithm, bipartite, and bipartite plural. So you see the elements there listed from D to D1 to D100. These are the demand elements, and those are then matched with using the different algorithms to match with the supply elements. What that means is we are able to use a catalog of existing steel beam members and identify where they might fit into newly generated design options for industrial buildings. So essentially what we do is we combine the generative design process with those matching algorithms so that we are able to supply the correct fit of the existing steel member into a design of a new industrial building. And it's not an easy thing because obviously industrial buildings have a very large span. So you do have to be quite particular in where you can reuse these steel members. But we also want to extend this not just to industrial buildings, but also commercial buildings, because most of the steel reused happens in areas such as densely constructed cities like London, where there is increased pressure to reuse steel. So what you end up with is having various different iterations of designs, but also being able to accurately match your supply and demand steel beam members. Again, I'm not going to bore you with the maths here, but the final outcome is this is our initial proof of concept of a web-based generative design tool where you have an interface and you're able to modify, in this case, an industrial portal steel frame design and then match that with a set of catalog of steel beam members. So in an ideal scenario, you would also want to potentially combine this with other information that this is where I see blockchain in particular will have value, is being able to guarantee and have a track record of the provenance of some of these steel members, because it's not just being able to have a track record of where that steel comes from, but it's also an interesting story that many developers and building owners are interested to know where that steel comes from. It makes for an interesting story to tell if your steel beam comes from, I don't know, some older, very famous architectural gem. So provenance is really an important part of, capturing the materials, where they've come from, and having that digital thread in some essence of your steel frame building. So, right, I'm going to summarize this in brevity because unlike to most speakers, I'm going to try and stick to that 50-minute rule as we are. I respect everybody's Sunday, so I want to capture this in the next 2 minutes. So really what we're trying to do here is to try and ease the way in which structural designers can implement reuse of steel members into the design tools. It's early days and our technology is at a low technology readiness level, but I would welcome people from today's conference to actually come back to us and discuss ways in which we could improve provenance for steel reuse through the use of blockchain technology and also smart contracts. So, for example, where I see it has great value is enhanced traceability for reclaimed steel. So to have an immutable record of the steel component's origin, property, history, I really believe that that could be a way that can be kind of carved forward together with some of the technologies that I've seen displayed today through some of the presenters' work. And it really could help boost the transparency in the supply chain, especially if we were going to do something like real-time tracking of steel through the supply chain. This is where I think it would have greater applications. So I welcome anybody to reach out to us and to find ways in which we may be able to merge some of the findings from our research work, and who knows, maybe even extend it into a new research project together. And finally, a shameless plug into our upcoming book on digital twins. So there's about 15,000 definitions of what digital twins are. Every industry has its own understanding of what that is. But myself and my esteemed colleagues, well-known academics in the built environment, we've spent the last 2 years debating about it. And now we've converted it into a book where we explain where we think digital twins will head for the built environment and how we see it as more of a digital twin systems for the built environment. So it's kind of a generic overview for the built environment to really try and understand what are digital twins and where the value can be derived from. And with that, I believe I'm only 25 seconds over time. So thank you, everybody.